Hello everyone, and welcome back to the Kohi Game Engine series. Today we're going to be wrapping up our math library by tackling matrices and quaternions. Before we jump in, I'd like to take a minute and thank the supporters of the channel, starting with the partners who are Eearslya, Wensheng, and Caden. The partner is the highest tier of membership, either via YouTube or the Patreon page, so thank you very much for your support. I would also like to thank everybody else that is listed here on this screen for your support. It is greatly appreciated. If you wish to support my work, you can either join via YouTube memberships. There is a link in the description below to that, or you can take a look at my Patreon page, which is at patreon.com/Travis Roman. Okay, so before we jump into the actual code here, we need to take a step back and talk about this last type that I just mentioned that I haven't really discussed up to this point. So we've talked about vectors, we've talked about quaternions, and we've talked about Euler angles and directions, all that kind of stuff, right? So what are matrices? Well, matrices are, you can think of a matrix as almost a two-dimensional array, right? Where you have numbers that are arranged kind of like this, that are used to transform data in various ways, depending on how the matrix is laid out and how the multiplication is done. And so matrices provide all kinds of things for us. They hold data such as position, rotation, and scale, otherwise known as the transform of something in world space. They can be used to project a three-dimensional object onto a two-dimensional surface. And there are plenty of other uses of matrices, right? And so we're going to touch on some of the basic types here. And note that this example is what's called a 4x4 matrix, or matrix 4 as we're going to call it, which means that it basically has 4 rows and 4 columns, right? However, this is not necessarily the only type of matrix that exists. A matrix can be any number of rows and columns. So technically a vector is a single row or single column matrix, depending on how you want to think about it, right? So this is a vector, this is a vector, this is a vector, this is a vector, and this, each one of these are also vectors, right? So a vector is a matrix, okay? And a matrix can be a vector. So like I said, the type of matrices that we're going to be primarily working with are going to be 4x4 matrices where there are 16 total numbers, or 4 rows by 4 columns, okay? And so these are what we are going to go ahead and set up and represent. Now, before we jump into the actual code, I want to quickly discuss some of the things that matrices are actually used for. So I'm going to go back here to my paint, and I'm going to hop over to this graphic that I stole somewhere off the internet. And what we're looking at here is a couple of projections. And you heard me mention projections just a minute ago. What does projection mean? Well, if you think about the way that especially three-dimensional games are put together, right? You have 3 axes, X, Y, and Z, right? And you have these objects that are moving back and forth in space and interacting with each other. But ultimately, your monitor, your screen, is only 2 dimensions, right? It's just X and Y. And so we need a way to translate that to a 2-dimensional image that ultimately gets rendered on the screen. And in order to do that, we do what's called projecting. So you can see here that we have 2 types of projections, and there are other types of projections that we're not going to cover here. These are the main 2 that we're interested in for this engine. We may add others in the future, but these are the main 2. So the most common one that you might think of when you think of three-dimensional games is the perspective projection. And a perspective projection basically acts like what a camera would in real life, where it takes these objects that are in space and flattens them down to an image. Okay, and so we have the camera, which is basically the player's perspective, for example. And then we have what's called a near clipping plane and a far clipping plane. And it's basically anything that is between the camera and the near clipping plane is not rendered. It's considered outside of what is the view frustum. And the view frustum is sort of everything between these two planes, right? It's this near clipping plane and far clipping plane. So if there was another ball back here, for example, it would not be rendered because it's been clipped out, hence the term clipping plane, because it's beyond the extents of this plane. However, if it were only, say, half into this wall over here, we would see half the ball. And so what this does is a couple of things. First of all, this represents how we see the world, right? Where the further you look out into the distance, the wider range of distance left to right that you can actually see, right? And so this does something very similar to that. And there are various components that we can do to adjust how much that is. But basically anything that is outside the left, right, top, or bottom also does not get rendered. So in this example here, the red and the yellow ball get rendered, but the green one does not because it is outside of the view frustum or outside the view that we can currently see. Okay? And so what you'll also notice is when you look at things in space, things that are closer to you tend to be larger than things that are away from you, which tend to be much smaller. And a perspective projection matrix mimics that. So you'll see here in the near clip plane where this has been compressed to an image that the yellow ball is actually larger than the red ball. However, if we look in actual 3D space, they're the same size. And this is because the yellow ball is actually closer to the near clipping plane and thus the camera than the red ball is, so it appears larger. And the way that that's done is this space on the far clipping plane means that we're basically taking everything here and stretching it out. And by the time this gets flattened, that means all this stuff has to be compressed. And when that compression happens, that is what makes this smaller, this object further in the distance smaller, right? So even though this frustum gets larger as distance goes away, because the object is smaller in comparison to that clipping plane, it appears much smaller once these things are made orthogonal, okay? And so that's sort of a very rough explanation of how perspective projection works. Now the other one here is orthographic projection, which is much simpler. This is basically a flat projection. So it basically has a near clipping plane and a far clipping plane which are the same size. So all lines are parallel in space. And what that means is that the objects will be the same size, however it will look extremely flat. This is useful for various views in game engines like Unreal or Unity, or even in 3D authoring software like 3D Studio Max, where you're trying to look at wireframes from like the top or the left to get a sense of how things are laid out in space without being distorted by projection, perspective projection rather. And so we will be using this in sort of editor views versus this in the world view. I should point out that we'll probably also wind up using orthographic projection for the UI, because UI tends to be sort of a flat 2D thing that sits on top of the world. So that's another place where we can use this. So I hope that makes sense. That's the difference between those two. And the representations of both of these things are represented by matrices. So you will hear of something called a projection matrix, and we can have a perspective projection matrix and an orthographic projection matrix. And the way that those things are generated is slightly different between the two of them. And you take our vectors that we have in 3D space and you multiply them by these projection matrices, and they project that image into 2D space, which is then rendered by the engine. So that is essentially, for all intents and purposes, what we're going to be doing. So the first thing that we need to do is actually declare a type. So underneath our quaternion type, we are going to define another union type, which I'm going to call mat4u. And again, we have some of this SIMD stuff here, which we're not actually using right now. But the important one here is our F32 array of 16 F32s, right? So this that 16, the 4x4 that I was showing you before, right here, right? So there's 16 numbers here. This is how we're going to represent that in memory. Is we're going to have 16 floating point, right? And so that is all that our matrix is, right? It just holds 16 numbers. That's all it is. Okay. So in our math, we want to have what we call an identity matrix. And an identity matrix is sort of, you can think of it as the default matrix. And it just so happens, and this was not by accident, that this is an identity matrix. So an identity matrix has 1 for all of these. So the 0 index, the 5th index, the 10th index, and the 15th index, right? So this is the base for all matrix operations, right? All matrices basically start off as an identity matrix, right? And this basically represents a neutral scale, right? So we'll get more into that in a minute. And so what we do here is we create a new matrix, we zero out all the memory, and we're actually going to need to include k memory for that in just a second. And then we set 0, 5, 10, and 15th indexes to 1. And then that is what gives us this, okay? And so let's go ahead and include k memory. So we get that, okay? And again, this is inline. Great. So the first and most important operation that we have for matrices is multiplication. Typically, you don't add matrices or subtract matrices. You don't even generally divide matrices. The only thing you typically do is you multiply them together, and that is how you transform matrices or combine them to equal a combined matrix. So you might have one matrix that stores rotation of something, you might have another rotation or another matrix that stores position of something, and you might have another matrix that stores scale. And you can multiply the 3 of those together to get a single matrix that stores position, rotation, and scale. And so you can store all that data and actually a little bit more in a matrix. So if you think about it that way, you can see already how powerful these matrices can be. So when we multiply, we actually take these 2 matrices and we multiply them together and return a new one. So the first thing we do is we create a new identity matrix. And we're actually using some pointer magic in here to multiply the matrices. And matrix multiplication basically states that you take the columns of one and multiply by the rows of the other. And so that is basically what this is doing. It's iterating through the columns of one and multiplying by the rows of another and using a pointer and pointer arithmetic to move through that array. This is not something I made up. I should mention I believe I got this from the Doom 3 engine. I think that's the way this does it. And this is actually an extremely fast way to do it. In my tests, it was almost on par with using SIMD, so it's actually extremely fast. So basically, just know that that's what this is doing, is it's taking the rows of one and multiplying it by the columns of the other. Okay? Next is a function that we use to create an orthographic projection matrix. Okay? And I've filled out here sort of what all the various properties are, but you basically need the left, right, bottom, top, near clipping, and far clipping. And these are distance from the camera, right? And so this is the algorithm to create one of those matrices. And again, I'm not going to go into depth on how this works. If you guys are interested on how these numbers all work, you feel free to look those up, but I'm not interested in teaching that on this channel. So that is how you generate a projection, an orthographic projection matrix. And here is the method for a perspective matrix. So this one basically creates a matrix that is specific to projection. So it takes an FOV, which is field of view in radians, an aspect ratio, which is width by height, and then near clipping plane and far clipping plane, and it generates a projection matrix out of that. One other type of matrix that is pretty important is what's called a look-at matrix, which takes a position and says, okay, from this position, we want to look at a target in space. And then the up vector is basically used to coordinate that rotation-wise. And so what this basically does is, if you wanted, let's say, a head in 3D space to follow an object around and rotate, constantly looking at that object, you would put the head's position here, right? And you would put the object position here. And as this changes, the head will rotate around to what it needs to in order to stay looking at that. So that is how you generate a look-at matrix. Again, I'm not going to go into great detail on how this works. If you guys are interested in that, feel free to look it up. Okay, so the next thing that is kind of complicated is an inverse matrix. An inverse matrix is basically a matrix that reverses the operations of another matrix. So let's say, for example, you had a projection matrix that took something from 3D space and projected it down to 2D space, but now you wanted to take something from 2D space and project it into 3D space. You would use the inverse matrix to do that. Okay, and this is the algorithm to get the inverse of a matrix. There's no sense in going through and explaining this line by line. This is just the way that the algorithm works. It's just the way it is. So again, if you guys are interested, feel free to look it up. I don't particularly care to go into the details of how or why this works. Okay, so now on to some of the more common sort of operations. We have what's called a translation matrix, which takes in a vector 3 position and creates a matrix holding positional information. So this takes a identity matrix and then sets the 12th, 13th, and 14th components to the x, y, and z positions respectively, and returns that matrix. So you can use this to combine position with, say, a rotation or a scale later on. And when we go to actually fire this off to the graphics card, we're actually going to have to do some of this stuff. So this is how you create what's called a translation matrix, which holds positional information. The next thing that I want to point out is, because it's nice and simple, we also have a scale matrix. So we can take a vector 3 that represents the scale in 3 directions. And again, we just take an identity matrix, set the 0, 5th, and 10th elements to that x, y, and z. Now these 0, 5, and 10 elements might look familiar to you, because if we look back at our projection matrix, we have 0, 5, and 10. Note that these are all 1. It's no coincidence that these are 1s, because if you started off with a 0 scale, you have nothing, right? Because you multiply by 0 and you get nothing. Since these all work off multiplication, you want a default scale of 1, which basically says don't scale at all, treat it exactly how it is. It's no surprise that we have 1, 1, and 1. So these, incidentally, are the scale positions of a projection matrix, of a matrix 4. Okay, so that is the scale matrix. Next, we have a collection of methods which create matrices from Euler angles. And this is that pitch, yaw, roll that I was discussing earlier. So here we can return a matrix, contains a rotation for the angle in radians along the x-axis. So this is how we calculate that. We have 1 for the y and 1 for the z. And then we also have another method that takes in the x, y, and z in radians and calculates all 3. And then here we multiply them together in order. So we do x times y, and then that times z, and we get our out matrix. So if we wanted to use Euler angles, we can use them. However, in most cases we won't be. But there is one case we'll be using this, and I'll explain that when we get there. Okay, so that is Euler angles. The next thing is, I actually just realized I skipped a kind of important matrix operation here. So we have the inverse operation, right, which basically allows us to generate a matrix that undoes the matrix that we pass here, right? But there are also circumstances where we will need to flip the rows and the columns, right? So you basically take all the data that is in each row and you put it in the respective column. And that is called transposing a matrix. So we have this mat4 transposed, which takes this matrix and gives us the transpose value. And so basically what it does is, again, if we look at our picture here, so it'll take whatever is in this row and we'll put it in the column. And you'll notice that an identity matrix, by no accident, is technically already transposed, right? The transpose is the exact same as the base matrix itself. So if we were to take the 0th element from the column and put it in the 0th element for the row, obviously it's the same position. If we take this one, which is the second element of this column, and put it in the second element of the first row, we get 0, right? This one will go here, this one will go here, etc., etc., etc. Okay, and so there are situations where we are going to need the transpose matrix, so we want that in there too. I put that right above inverse. Okay. So after that, it would be nice to have a way to obtain some directions from a matrix, right? So we have sort of these matrices that can represent position, scale, and rotation, right? But what if we wanted to, for a particular orientation, what if we wanted to get sort of the forward vector, right? Like, for example, let's say we had a camera in 3D space that was rotated by 45 degrees on the x-axis and 45 degrees on the y-axis, and we just want to move it forward in the direction that's currently facing. We don't immediately have an easy way to do that, and so I'm going to go ahead and just paste some methods here that give us that capability. So we have mat4 forward, which extracts a forward vector relative to the matrix that's passed in, and you'll see where we wind up using this later on. We have backwards, which is basically the same, it's just a reversed vector essentially of the forward vector. And then we have up, down, left, and right. Okay. And again, feel free to examine these to figure out how they work. They're not too complicated, but I don't necessarily want to take the time to explain every single one of them. Okay, so that is the major functions that we need for matrices. Okay, so the next thing that we need to worry about is our quaternions. Quaternions, first thing we're going to have is a quat identity. So similar to how matrices have an identity matrix, quaternions actually have a quaternion identity as well. And that is 0 on the x, y, and z, and 1 on the w. Okay, and that is sort of the default or identity quaternion. Okay. The next thing that we will want is the ability to obtain the normal of a quaternion. So it basically just takes the square of each of the components, adds them together, and then takes the square root of that. So that is the normal. We also want the ability to normalize a quaternion, right? So we just return the normalized copy of that. We are on occasion going to need what's known as the conjugate, which takes a quaternion and flips or negates the x, y, and z components, but leaves the w alone. On occasion, we are going to want the inverse of a quaternion. So all that is the conjugate of the quaternion, and then we normalize that. So it's pretty straightforward stuff. Next, similar to matrices, the only way that we typically deal with quaternions is through multiplication. So again, we don't really add them or subtract them or anything like that. We typically just multiply them together. The multiplication for quaternions is pretty set in stone. There's really only one way to do this, and this is it. So I'm not going to walk through this here. Feel free to look this up if you want. the formula is the formula, right? Next, we want the ability to take the dot product between quaternions. So it's basically, again, the difference between quaternion 0 and quaternion 1, and we return that as an F32. And then, of course, we need a way to take a quaternion rotation and output it to a matrix, right? So we had a way to do that for Euler. Now we have a way to do that for quaternions as well. So we take an identity matrix, we normalize it, and then we fill out all the data using this. And for those of you who are interested, this is based on the Stack Overflow article that I found here. It's pretty good reading on how these conversions work between quaternion rotation and rotation matrices. So I figured I'd leave that note in there for anybody that's interested. Okay, so we have quaternion to matrix 4. However, there's also a variant of this that is useful as well. And that is we have this quat to rotation matrix where we take a quat, but we also take an center. And this allows us to calculate a rotation matrix based on the quaternion and the past and center point. So we basically take the rotation and we calculate a matrix based around this center point, right? So we can rotate around a center, for lack of a better term, right? And this is the calculation for that. Again, it is what it is. I'm not going to explain it in depth here because this is not a math course. Next, we want a quaternion from axis angle. So this is essentially an Euler rotation. So this allows us to take an Euler, which is a little easier for humans to understand, and convert it to a quaternion that we can then use. And so this here takes the axis. So you could say the axis is, say, the y-axis with positive on the positive 1 on the y, and then the angle along that axis to rotate. And it takes all that and converts it to a quaternion. You can also optionally normalize that here. So if you normalize it, it'll do it in line and return it for you. Okay? All right. The other thing that I'm going to add in here, but not explain in depth, is basically the spherical linear interpolation between quaternions. So basically what it does is it says, okay, we want the quaternion rotation that is between 0 and 1 at this percentage. So if we were to pass 0.5 here, we would say, okay, well, what is the half of the rotation orientation between 0 and 1? And we would return that. Here is a Wikipedia article on how that works. And a couple of notes in here that only unit quaternions are valid rotations, so they have to be normalized in order to work with this function. And basically this is the code to actually handle that. So again, not really interested in explaining this too much. Just understand that that's what this function does. If you're interested in reading that, certainly have a look at this Wikipedia article here. Okay? All right. Now we're done with the heavy lifting of quaternions, right? So there are a couple more small things I'm going to add at the very bottom here, which is a deadtored, which takes degrees and converts to radians using our multiplier, right? So it just takes in these degrees and multiplies that times our deadtored multiplier and returns that value. And then we have the opposite to take from radians to degrees. This is just sort of a convenience function. It's inline, so there's no cost in using it. You can just do this inline, or you can use this function to do it for you, and it inlines it anyway. So that is pretty much it. The only other thing that we'll need to do is at the top here, we defined some functions here, these guys, and these that are not inline, but we never actually defined the functions. So we actually need to fill those out in kmathc. So obviously we include kmath.h, and this is where we're going to include math.h, right? Because we don't want to include it in the rest of the engine. So after that, we are going to go ahead and fill out the definitions for these guys, okay? And so these are one-liners, pretty straightforward. They just point to the math.h implementation, right? So ksine uses sine f, k cosine uses cosine f, tan, f, a cosine, etc. Right? It's pretty self-explanatory stuff. And this allows us to, again, use math.h locally here and not have to use it everywhere else because it's kind of big. And next we have our random number generators, right? And so the way that random number generators work is they're what's known as pseudo-random number generators. They're not really random. And we're going to start off by using just the srand, which is in the math library. It's not a very good random number generator, but it is one that we can use for the time being until we are ready to at least make one that is a little bit more robust. So there's a couple things we're going to need to do this. The first thing that we're going to want is we're going to want to include platform H, and you'll see why here in a second. And we are also going to want to set up a static variable called random seeded and set that to false. Because anytime you use a random number generator, you have to seed it with a certain value. And by default, it is not seeded. So what do we mean by this? Well, if we look at this, we have krandom, and range. So we're going to fill out these guys. So we have I32 krandom, and then we first check to see if we're not seeded, right? So if we're not seeded, then we call srand, which is seed rand, and we get the platform absolute time. So we're going to use the float 64 absolute time. We're just going to cast that to U32. And that's going to give us sort of a pseudo-random seed, right? Because the time is always going to be different whenever we call this. And so if we haven't seeded, we're going to seed it with the platform's absolute time. And then we'll go ahead and flip this flag to true. And this will only have to run once. Otherwise, it just returns random using this seed. Okay? And that's basically the way it works. The random and range is a little bit more complicated. So it does this same check. And then what it does is it takes the random and it performs a modulus against the max minus min plus 1, right? And then takes that entire value and shifts it over by min. And that, in turn, gives you a random number within this range, okay? And then, as you may or may not have guessed, the float variants are the exact same thing. They just are floating point equivalents. Now I see here that our random max is not filled in. That is because we need stdlib.h, which actually includes that. So you can kind of see why I didn't want this sort of exposed to the rest of the library, right? So this is pretty much it for our math library. I believe that is it, actually. So let's go ahead and build. Just make sure that everything builds, and looks like we missed a couple things. So let's see. Type name. Oh, okay, it's complaining about the align as. You know what? For the sake of this video, I'm actually going to take the SIMD stuff back out of here. And we can end that. We can always add that back later when I'm ready to discuss SIMD. So I'm going to go through here and remove that. Let's try building one more time. I think I've got to remove it in the other later on in the file too. Okay, that's fine. All right, so we will handle the SIMD stuff in a future video anyway. So it's kind of a nice little teaser for you guys out there that know what that is, and we're asking whether or not we're going to implement it. Yes, we are, but just not yet, right? We're going to optimize much later. Okay, so we've built successfully. We now have a math library that we can use with our engine. And so this is actually where I'm going to go ahead and stop this video for now, because the next one is going to jump back into the renderer, where we are going to start setting up some Vulkan specific things using this new math library and math types. And we are going to go ahead and start working on, or start working toward getting something on the screen. So with all that said, thank you guys so much for watching. I hope you enjoyed this series. I hope you learned. If you liked the video, please toss it a thumbs up. Go ahead and subscribe if you haven't already. And ring the little bell notification there to get updates on when the next video in this or other series drops. And I will see you guys next time.